Hello viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about battery versus hydrogen trains in 2025. So let's dive deep into it. Now, electrification. Under known science, and let this be very clear, that simply means from now to forever, unless some super duper hyper new technology happens like teleportation, under known science is the best in terms of energy efficiency. Meaning, if I give you 1 megawatt hour from a power plant, whatever that power plant be it solar, be it wind, be it coal, be it nuclear, does not matter. Power plant and how much energy will go to your wheels moving the damn train, that would be 85 to 95%. That is the highest we have managed to achieve so far. Everything else will assume this as 1 and it will be lower than this. Let that be very clear. So if you have electrification, nothing beats it. Now, if a country invests into basically electrification like India did, it is the most long-term green option. Meaning, once you do this, over time, it will become better. Over time, it will start to pile off. Oh, you are saving a little bit of diesel. Oh, you are saving a lot of diesel. Like over time, it will be like, yeah, there is a big environmental and all that impact is there. So fundamentally, it's a good thing. Then you're like, okay, if it's that good, then why don't everybody? It's expensive AF when it comes to capital investment. And even the maintenance is also not free. So yeah, it's expensive. Now, what does that mean? And if it is that expensive that even Japan cannot do it in 100% or Germany can do it 100%, why did India manage to achieve such a high level of electrification? Be mindful, this is very good electrification, and India has reached around 97% by 2024. This map is a bit old, but again, these parts are messy right now, but we will sort it. Trust me, we will sort that puppy. So India is making such a good progress. Why? Why this is such a unique case? Again, China is also doing some good progress. Not USA, not Europe. Then question is like, why? Well, India has lack of oil security. Meaning, if we are running all these puppies on diesel, there is an issue. Someone in OPEC controls our food prices and our livelihood prices. That is not acceptable for a nation. Now, like, okay, if India does not have oil and gas, how would you run electrification? Well, coal. Now, at the core benefit with coal is that we control it, meaning these states have more than enough to run the nation. So that was the whole point. Because we did not have oil security, we jumped very early on electric, and we did not be like, okay, only high speed links. No, everything will be electrified, and we went all in. Now, there is another reason for that. Another reason is population density nation-wise. While you can see like, oh, Tokyo is so high density. Yeah, Tokyo is high density. Japan is not. And same goes in Germany. You can find Frankfurt to be very high density, but does not mean the whole Germany is high density. And India, it's in one of those unique places where everything is high density, in contrast, so to say. So it kind of justified. Basically, we had to have electricity there, we had to have power plants there, we had to have grid there. So it's like, might as well just add this. And overall, India's goal aligned with this desire. So things worked quite well. And there is one tiny good thing that also happened is that it makes Indians feel very proud. Yeah, we do not have that many thefts. Now, again, you have to understand, we are talking about almost 1.5 billion people. So even very tiny percentage of people would be ludicrously large population. But we have surprisingly little theft. Now, in contrast to what? Well, Pakistan also learned the same thing, is that if they are buying oil and that oil is used to run their trains would be a very serious jeopardy. So they started investing in electrification. They bought a lot of copper wires. Yeah, people stole it. They're gone. Done. Poof. Same happened in South Africa. Same happened in some other countries. Even Brazil suffered a lot of theft of that copper wires. Like, it was so bad in certain places that they had electrification. People somehow managed to figure out how to steal electricity while it was on. And then the company just gave up. It's like, yeah, we cannot keep replacing it. There is like, those are expensive. Overhead wires are expensive. So, and again, downtime and all that. So they just gave up and switched to diesel. So India does have this going on for us, that we have such a large network, like ludicrously large network, and surprisingly little theft. So that did pay off. On top of that, if you go to places like Germany or Japan, where it's like random location, even UK, random location is like does not have electrification. Why? Even though from a country's point of view, don't you have done electrification like long ago? Problem is there, it's hard to justify our branch routes. Like for example, in France or in Germany, you're like the main link, TGV link, go YOLO on it, no problem. Oh, this is this like random small town, small village. Yeah, we cannot justify a few $1 million per kilometer of electrical overhead or third rail. So for that reason, it's not justifiable. And same happens in Japan. They have Shinkansen going YOLO on it, but remote location, poof, surprisingly large amount of them are diesel. So it's hard to justify for branch out. Now, India went all out, but other than that, this is still the edge case, so to say. Electrification is the best, meaning if you have a limited energy source, this is the best way of doing. And again, India, because we jumped so early into it, now we are switching to solar, so all our railways are also yielding good results. Once we have a bit more wind power, it will be even better. Nuclear, even better. We can keep adding things to it. So we are sorting the foundation and we are making good progress. So what happens after that? Well, where is the conversion? Well, conversion under laws of physics, meaning it will not change. I cannot tell you how many times people have commented, it's like, oh, those were like, 90s, 80s technology, today's is better. No, if certain things are done, the penalty would be the same. Now, you can reduce the penalty, but penalty will always be there. For example, under known laws of physics, it's very clear that if you convert, you lose some percentage to waste heat. Like no matter what you do, if you convert, basically, let's say you take energy that is flowing from a generator, electrical energy flowing from a generator, dump it into a battery heats up, you have waste energy there. Now again, percentage will be low, you can reduce its impact, you can do a lot of things, but you will always have wastage. Now same way, when you go from like phase, similar kind of phase to complete transformation, for example, going from electricity to gas, like in case of going from electrical power plants to hydrogen gas, that will be even more wasteful compared to chemical energy that is like almost like electrostatic energy, and that electrochemical energy going into electricity again. It will be, it's on fundamental level, you cannot change it, it will never ever change. So that's there. Now what does that mean for you and I, or for railway corporations that are paying for this? Well, round trip efficiency, they have to calculate that, because here's the deal. For example, if your train requires 1 kilowatt hour, now of course electric almost is going to give you that one, like let's say 1.2, little bit of buffer and all that. So if your wheel traction motor needs 1 kilowatt, cool, battery is going to consume a bit more. Now when you talk to hydrogen, it becomes almost 2.9, and they are way too optimistic. So you take 2.9 kilowatt from the grid, 70% of it would be converted into hydrogen, 30% would be wasted. Now be mindful, this is phase change and transformation. Fundamentally, this cannot be made too much efficient. If any Tom, Dick and Harry says you, we have this electrolyzer that is 95% efficient, run. So electrolyze, it will happen. It does not matter if it's for 1970 or it does not matter year 5000. It will always be wasteful. Then you can compress the hell out of it. Now how much you compress, that's up to you. In this scenario, they are very gentle, 350 bars. Generally you may want to push it to 600 bar. Again, penalty would be, this step itself will consume a lot of energy, so this step not that bad, but again, if you increase the compression, it will become bad. It's 91%. And then you send it to, they remove the transportation part. I'm like, what? But okay, then it goes to fuel cell. So your hydrogen tank to fuel cell, that puppy will only give you 60%. That's fundamental. Like these two jumps, basically going from chemical to electrical to again chemical to electrical, yeah, that part is the most wasteful, and you cannot reduce this. Like some amount, of course, some amount can be reduced, and generally I've seen the majority of the fuel cell development is like how long can it last, how cleanly it separates hydrogen and oxygen, how much contamination. Those things are improving, but the thermodynamic efficiency, yeah, it's not changing that much. So this will be, and then you will have electricity, it will go to converter, generally VVFT, and then you will finally drive the wheel. And you are paying this much, 2.9, almost 3 to get 1. That's why round trip efficiency matters, because again, your train will consume based on its motor. Motor is like, bro, I need this much power, that means I need that much power. You cannot reduce it. So if wheel needs that much and you are wasting so much, that means you are paying every trip, every time this puppy is moving, you are paying exponentially more. So that's why round trip efficiency matters far more than you realize, because again, it's every trip is like, ooh, it hurts. Now another aspect is capital. Again, same way, if electrics were cheap enough, we all would have done it. But capital investment on hydrogen systems, it's very high. It's almost reaching a point where it's like, might as well bite the bullet and get an extra loan and just finish electrification. But capital is not that low. Like hydrogen, you would think, oh, it's not that expensive, it's a 1970s technology. No, it's not quality technology, so to say. So it's very expensive. And again, that's why Japan is running so many electric battery trains. So the idea is it becomes an electric train. They have pantograph when you are go to electrified line, and when you are going to remote locations, only the stations have that pantograph where you just like charges the battery for short duration. So they have a lot of it running for a very long time. And then they started to have battery on their diesel system, diesel battery hybrid. Again, that's also very efficient. This is complete battery, but that's why, again, round trip efficiency matter, because they are paying for it. So if they did this whole thing with hydrogen, the paying, basically every time they had to pay the grid department is like, hey sir, how much? Yeah, it will hurt every trip. So that's why round trip efficiency for this sort of system matters far more than you realize. It's not something that is like, who cares? And there is no such thing as surplus energy. I have no idea how the heck this engineering team lost all its engineering. Surplus energy simply means at that time you do not have demand for it. We do not live in a world where you have electrical wires and sun gives energy to it. That's not how it happens. You buy bonkersly large amount of solar farm. You built bonkersly large amount of inverters. You built substation. Then you connect it to the national grid. And then if you are lucky, you have some time where everybody is producing and not enough demand. That's what surplus means. Surplus does not mean free. Surplus simply means you have inefficient grid. You do not have energy storage. And it's never free. You cannot afford to waste it. You cannot be like, oh, it's surplus, we can just waste it. Yeah, the moment everything else catches up to it, yeah, that I have no idea how the heck that happened. Genuinely, I'm sorry. Like surplus, it's like surplus does not mean free. Surplus simply means for that moment, it's there is no other demand on it, and that's, again, that should not happen. That simply means you have no energy storage. So let that be very clear. Conversion matters. Round trip efficiency, every trip matters. And again, if you are doing this for, let's say, these sort of puppies can easily work for 20 years, 30 years. Yeah, this wastage will pile up so quickly, you'll be like, what was the point of doing this? Now let's understand the powertrain of it. Now, traction motor, that's your main puppy. That's the one thing that runs. Then you have VVFT. Now, again, not necessarily everything has VVFT, but generally you will get variable voltage, variable frequency drives nowadays. And then where does that pull energy from? It pulls energy from battery. And like, wait a minute, hydrogen, why the heck there is battery? Yeah, it has to be. So it pulls energy from battery. Battery pulls energy from fuel cell. Fuel cell pulls energy from hydrogen. Hydrogen pulls energy from the compressor. Compressor pulls energy from electrolysis. And again, there are far more steps, but you get the point. It's a long energy train that you have to follow, so to say. And then compare that to battery system. You have traction motor, again. You have VVFT, same. You have battery, same. Done. After that, it's a grid source. Or sometimes, again, I will talk about that, what Britain is doing. You have bigger battery. If you wanted to surge charge it, this helps. Done. Done. Go home. There is no conversion. Done. Go home. So fundamentally, you cannot compete the round trip efficiency. Future technology will not change it. Now, one core benefit, let us be very clear, there is one core genuine benefit, is that train will become heavier with battery system. That is factually true. Now, that is factually true, but here's the ironic part. Train is one of the few mode of transportation that does not actually hate weight. Meaning you may likely to have a scenario where your train is slipping rather than it's like, oh, it's too heavy. So ironically, it's one of those things where it's like adding few extra tons does not translate to it's useless. It's not like electric car or electric bus. Like electric pickup trucks, they have huge batteries. Some of them have like 300 unit battery, like 300 kilowatt hour, and they do not travel very far. Now why? Well, because the battery is so heavy. Train will not do the same thing. The rolling resistance, the benefit, the steel on steel will allow you to still travel very long distance, and because of improvement in traction due to weight, you may actually get a really good performance. So train does not hate weight. Now, would you like to have a lighter train? Absolutely. Meaning if you could design a new train, you may design in such a way, hey, instead of using metal, let's use fiber and save all the weight and put the weight into battery. Because again, there is a scenario where you make train too light and it starts to slip. Happens way too often. So train does not hate weight. Again, if you make it lighter, yes, it will help in high speed. But whenever you are talking about hydrogen or battery, you are not talking about high speed. Because if you are stupid enough to like, okay, I'm going to travel at 350 km per hour like TGB or something even faster than that, and I'm going to do that on hydrogen or battery, yeah, people are going to take a missile and put it up your ass. That is not viable. So generally, whenever you're talking about, you're talking in remote locations. Sometimes speed could be as low as like, 50 miles per hour. So train does not hate weight, especially in those sort of speeds and category. Light trains have traction issue. So this is a powertrain from a real world, a real scientific documentation, real world locomotive. It's like you have hydrogen fuel tank, you have fuel cell stack, then you have converters, then you have a DC bus, then DC bus goes into the VVFD, then VFD drives the motor drives the wheels. Now here's the deal, because train is so big and heavy, it cannot actually have a brake that can slow it down. So all the trains generally take the wheel, drive the motor as a generator, gets the excess energy. Now back in the old days, we dumped that energy into resistor banks. Those heat up, dissipate the heat. Now, and yes, let that be very clear, you can apply brakes at high speed train, it will stop once. So that's why without brake resistors, there is no way. And we figured out brake resistors very long ago. Like, you will be shocked how long ago we figured this out. Basically regenerative braking. Now, if you have a battery system, now you have the ability, instead of brake resistor, you send the power back into DC to DC converter and it goes to the batteries. And battery also allows you another benefit, because again, acceleration energy can be recovered. So let's say you spent 10 units of energy accelerating the train, you can, in good days, can get almost 3 to 6 units of energy back while decelerating. So, and again, it also allows your brakes to last much longer. So that's the good part. And this also gives the fuel cell buffer time. Fuel cells are mechanical devices, meaning you have valves. It's almost like an engine. So it has a flow rate and all that. So even if you send the electrical command, boom, give me more power, it will take time. Batteries are like, I got you. That's why electric cars are so responsive. Like, you press the accelerator, it's just the computer at that point in time. Meaning computer is like, if it thinks like, oh, you really want to go, it can out accelerate a Ferrari and Lamborghini, because just battery is like, I have the power. There is no conversion here. It's like, I have the power, electrochemical power. It's like, as long as I have conductors that are strong enough to dump that amps, I got this. Me good. So that's why battery energy storage is kind of compulsory. No matter which brand of train you are looking into, generally they have a hydrogen tank, fuel cell, auxiliary converter, traction converters, and traction motor cool, and then there will be battery. So basically, whenever you are looking into procuring a hydrogen train, it's a battery train whose battery is small. Yeah, so if it was just running on battery, I don't think it will run for more than 10-20 kilometers. But it is a battery train, fully kitted out battery train with instead of having larger cell capacity, it has small cell capacity, and instead of basically bigger cells and batteries, electrolytes, you have fuel cell and hydrogen tanks. Weight is the advantage that you gain. Other than that, you do not gain anything. But again, in certain scenarios, weight is not that detrimental as you would think. Like, again, it's very detrimental for road vehicles. For trains, not so much, especially if you are living in a country where leaves are an issue. So this is the powertrain. That's why hydrogen trains are so expensive. It's like, it's a fully built electric train, then on top of fully built battery train, then you have hydrogen systems. Yeah. So what about this battery system? Now, this is a newly installed system. Be mindful, battery trains are ancient technology. This is just a recent, as in like 2024, end of 2024, in real world service, meaning if you are living in UK, if you know where to go, you can actually ride in this puppy. So they are designing a train, and their selling point is really fast charging technology, meaning nothing inherently is like wow. It's just that given the constraint they had, they decided jumping on fast charging. So the idea is, they're going to take a grid, they're going to take solar, they're going to dump it into trackside batteries. So this trackside battery would be generally in places that does not have strong grid. The energy requirement of these train, like that burst charging, it's high. So if you have good grid, it's not an issue. It's like, grid is like, bro, I got this. It's like almost like a big furnace turning on. It's like, I got this. But if you are in remote location, you do not have that kind of oomph, you will need a trackside battery. And benefit of trackside batteries, if you have that sort of battery, putting solar makes sense. Like, solar's biggest weakness is battery. If you need battery, might as well add it. So from an economics point of view, it justifies it. So you have grid, solar, you can even have wind turbines, you can have like whatever local energy source you can have, or you can even have a generator as a backup in case of a failure. So all those things goes into trackside battery. Trackside batteries is just shipping container with up to 2 megawatt hour of storage capacity. And it does have the ability to dump that energy. The core point is, it should be able to dump that energy. The energy amount is not huge. The ability to dump that much energy that quickly is huge. So train stops. Okay, now here's the deal. The train stops in UK is designed in for 3 minutes 30 seconds. So the idea was that they should be able to transfer as much energy needed in this time window, actually less than this time window, because train stops, the stopwatch was, but after that the foots that are going to collect energy from the track will connect down. So it may actually need only 3 minutes. So you have to dump a lot of energy. And once the train leaves the station, so train comes in, deploys the foot connects to the power rail gives them the energy, train charges itself, and 3 minutes 30 seconds later, everything rails disconnect, train moves on. Then you start to trickle charge the trackside battery. Now where do you put this trackside battery? Again, depending on your location. So based on how frequent the trains are, based on how much energy you need to store, how much energy you need to buffer, you're gonna figure, like, so you can have 2 trackside, 4 track sides. Two. Most of them designs I've seen is only about 2, and it's nothing fancy. It's just a container. It's just a simple container. So the idea. And what about battery capacity? The trains have 504 kilowatt, like almost half megawatt hour capacity, which is significant. Now, is it very huge? Not really. It's almost like some pickup trucks almost touch half of it, or almost 1/3 of it, and some buses have this sort of. So it's not huge. And in terms of surge charging, how hard they are pushing? First, I thought they must be pushing very hardly, and then I looked into the numbers. It's only 2 to 3 C, meaning there are many lithium chemistry that can easily handle that. Lithium iron phosphate can handle some amount of this. Lithium titanate oxide is like, bro, don't even bother with me. Although nickel, manganese, cobalt cannot. If you do that, that will hate it. It will overheat too quickly. So, of course, they will fine tune and select the chemistry precisely with the requirement. And be mindful, they know. There are 2 ways of solving the battery quick charging. You just brute charge it and cool the battery, like how you do it in Tesla, or you have a chemistry that can handle it. Penalty of those chemistries are generally capacity goes down, meaning your kilowatt hour is less. So for example, if they had magnesium batteries with nickel manganese oxide batteries, they would require cooling, but they can charge at that speed, and the 500 will become most likely 7 to 800. So, but again, that is far more vulnerable to catching on fire. It's a train cannot catch on fire, so they have to use a chemistry that is far more suited for it. So it's a bit of balancing act. If you use lithium titanate oxide, you get completely fire safe batteries, and again, it also easily able to handle 5C. So it's like, this fast charging is like, bro, wake me up when you have something interesting to talk about. So that's not an issue, but capacity goes down, so they have to balance this. And trackside batteries are not that big. And what about the energy? They are talking around 750 volt, which is not that huge, given the fact that even India has metros that whose third rail is at 1500 volt DC. So this is not that high. And be mindful, if the wear and tear would be far less, because again, it will only deploy when it's static. So it's even better compared to, like, a third rail contact. So, and shoes are almost same design from third rail, but they are moving. So that's the different part. It's actually moving. And the design of the third rail is surprisingly clever. So the idea is, it's almost like this. So you have positive rail, ground rail, ground rail. Now here's rail. Your train has like this. So train goes. Now when train returns, it comes like this. But it automatically switches. The center will always get the positive. So it's a very clever. It's like somebody thought of it. It's like so clever idea. Like, hey, what if we had only one positive rail and grounding on both sides? So train going up direction, no problem. Coming down direction, no problem. Such a clever design. So this is a very clever thing, nothing magical and nothing. And again, even this coach is from their underground network, and there is a very nice gentleman who is giving you all the technical detail, and he's very clear. It's like, there was other company that did try, they did went bankrupt because they were trying to pull coaches that were 50 tons, steel coaches. These coaches are made out of aluminum, so this puppy can reduce the weight by 20 tons. They are adding 2 to 3 tons of battery, so it's not that big of deal. So that's why they are getting such a big, and again, lot of improvement, lot of thought put into this. And there is amazing video about this from Electric Charge. I have linked the video down below, where they have almost behind the scene for 2 years of this thing. They built the shoes, tested the shoes, put it on a track, tested the tracks, tested on a dummy train, then tested it on a real train, and now this train is real use. So this is amazing. This is very clever. It's like, hey, we need solar needs battery, might as well put battery on the side, trickle charge the battery, so it's not a very big drain on remote location grids, and voila. And again, the shoe designs are awesome, because again, you're like, oh, this will wear down. Have you seen a third rail? From third rail's point of view, this is like, bro, I'm sleeping. And yes, third rail also has a mechanism that allows it to like maintain contact on a wavy track. So this is a very clever use, and design in such a way that they only need to do it once or twice. They do dump energy like 300 kilowatt on one battery bank. They have 2, so almost 600 kilowatt. So it's a powerful puppy. So this is a very unique way of doing it. You can put it, and again, 1, 2, 3, 4, 5, fifth, then again they have. So based on the design, they will make sure that you will never run out of batteries, so to say. Now we come to the sad part of India's hydrogen train. Now, the same makers who have designed India's basically high-speed rail, not high-speed, it will be semi-high-speed, Vande Bharat Express. It's a good train. And again, in Jind to Sonapat, it's a location which is already electrified. That's like rubbing salt on the wound. Electrified route, they are running this hydrogen train. Now, his deal. India already did hydrogen train, again, as in like the prototype testing phase with a toy train. Now, in our mountainous region, we have a toy train network. It's a very small network, very like scenic kind of thing. It's not like people mover. It's more of like, scenic, enjoying, having fun. So in those locations, you cannot do electrification. A, that's not printing that much money. B, you may not want to change the scene. So they are using hydrogen. It kind of makes sense. Again, battery will be far better, but okay. And now doing that in a place it already has electric, and this can go to 110 kilometer per hour. Be mindful, India does have semi-high speed train which travels more than that, 120 to 150 kilometer per hour. I'm pretty sure the motors will be hatefully looking up. It's like, bro, we have a 25 kV line there, man. Just put a pantograph, just give me that energy. And efficiency also. And I'm pretty sure Indian grid department is like, bro, you do not have, basically our railway department does not print money. So it's like, bro, you're running on loss and you're burning energy away on hydrogen BS. Does not make sense. So toy train was somewhat logical, at least. Okay, you cannot electrify it. Okay, this is electrified. This does not even make sense. And how government is justifying it is like they are building tech so we can build more. It's almost like same stupidity that Japanese government did with the maglev system. Maglev has been going on for a very long time. It's like almost 1980s. They're like, we're going to build maglev so we can sell the technology to other countries and all that. Most countries looked into it and looked the price per kilometer track. Yeah. No. And Japan kept forcing it. Most people have already given up. It's like, yeah, this is a bankruptcy white elephant. It's like, you can make it. It's just like, there is no point of it. So, because again, you have to justify, you have to pay that money back. And even in principle, you cannot pay back, then there was the point. Like, I get it, always put everything in the future debt, but you can't do that like open, yeah, we are taking this 1 trillion track line. I'm like, $1 trillion for a railway track. Yeah, it's not worth it. And again, it's not even traveling at like Mach 2 or something like that. It's barely traveling 100, 200 kilometer per hour faster, 600 versus 400. That's not that big of a difference. Once you cross 300 kilometer per hour, the time saved is not that magnificent. It's very magnificent from 100 to 300, but it's not that magnificent from like 300 to 600. So this is literally same thing. It's almost like, be mindful, Germany also did that. And I cannot believe how many people are sharing that photos. They're like, Germany is doing hydrogen. Yeah, they stopped it. In 2022, they stopped it. They built it, they tested it, and then they looked into the price. And then they looked into the round trip efficiency. And then they're like, yeah, it will be far cheaper. Because again, round trip efficiency, every time you're moving, you're paying that bill. It's like, yeah, it would be far cheaper to just use battery. And I'm like, Japan is laughing at the corner. It's like, bro, we have been doing that from 80s. So it's one of those things. So it's like how it almost looks like Armstrong. Like again, Armstrong has a good deal with Indian Railway, so technology transfer and all that. It almost looks like they looked at it like Germany is like, yeah, that technology is not paying off. Just slam it to Indians. It feels so bad. This line that scary is almost like we build BS so we can build more BS. Like round trip efficiency matters the most on something that has to pay for that bill for 10 years, 20 years, 30 years. And again, India has to maintain a fleet of diesel locomotives for two primary reasons. First, backup, because let's say something does happen, derailments happen, malfunction happens, things happen. That time you do need a way to recover things. Diesel locomotive, cool. Another aspect is Indian Army. Indian Army is like, hey, we always need something that cannot be compromised from a central oops point. So diesel locomotives. So India has to maintain a fleet of electric locomotives, the main daddy force, and then again they have to have small puppy force of diesel locomotive. Now we have to maintain a third force of hydrogen technicians, hydrogen locomotives, hydrogen BS. And again, it's almost a circular thing. It's like, why you're running hydrogen on main line when we have electric? So we can build the technology so we can run a toy train. Why does it just make it into a battery system? And again, this toy train, again, it's a toy train. It's a scenic route train. It's not traveling at 500 kilometer per hour, baby. It's barely traveling at 50 kilometer per hour. So it's almost like forcing Indian government on that, because It's a vanity. It looks sexy. Let that be very clear. It almost looks sexy to a point where it's like, look, we are doing hydrogen. Again, same way, everybody share the images of like hydrogen, Germany, and nobody shared the images when they're like, yeah, this was stupid and we cancelled it. And again, they did amazing research on that. Like you can read the papers of that. Again, half of the research paper I'm sharing, it's from Britain and other countries also. A lot of research, you can read it. It's like, yeah, this will not work. It's scientific notations and physics. It won't work. But forcing third option, vanity, looks cool, sexy technology, and it's almost a top-down plan. As somebody on top, like some minister got like, oh, hydrogen. I'm pretty sure Amsterdam, they're like, sir, hydrogen. This technology is awesome. It's almost like Japanese trying to sell maglev to other countries. It's like, sir, maglev. It's like, but thankfully in maglev, at least you can easily realize, wait, how many $1 million per kilometer? Yeah, no thanks. Me good. This for some reason can bypass that, and again, it looks sexy, and people are like, hydrogen is a new technology. It's older than lithium ion batteries. Lithium ion battery got into the patent realm in 1990s. It became mainstream from that point forward because it was a good technology. Fuel cell, we used a fuel cell to put man on the freaking moon. Apollo had fuel cell. Space shuttle had fuel cell. It's just after that we realized it was a stupid idea, so we just put solar panel cell battery now. So you get the point. It's been there. We've done that. Like people are like, oh, hydrogen. I told you, the thermodynamics will not change. You can improve how pure hydrogen it can make. You can improve how much separation you get. Basically, anode only gets this and cathode only gets that. That can be improved. All those things. And again, how long it lasts. The longevity of all the electrolyzers are horrible because again, you're corroding the metal there. So that is also a very big important point. But like in terms of actual thermodynamic efficiency, yeah, it's not going to change that much. Like we've been there. We built a hydrogen-based, fighter jet. We built hydrogen-based passenger. We built hydrogen-based combustion engines. We built hydrogen-based fuel cell vehicles. All of that has been done in 70s. It's almost like people forgot that you're supposed to read history the first step. It's like, has somebody built this? Had somebody learned from this? Thou shall not repeat the same mistake. It's almost feels like, cynical to a point where it's like, might as well burn this. Like, some European will look like, hey, dude, we dumped so much money into this, might as well recover it. This slammed it to Indians. And then once the bill finally starts to come in, it's like India would be like, hey, please print more money, more inflation. Because again, apparently we have very little inflation. I'm joking. We have painful inflation. I like paneer roll. That puppy is around 120 rupees right now. I'm pretty sure by 2035, it will be 300 or 500. Because if Indian government cannot burn money, especially on a branch that does not print money. So this is really painful. So this was my presentation on basically hydrogen train versus battery train in 2025. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.